Welcome to all of you. Now we discuss about multiple choice question 2020 for linear programming problem and game theory paper semester 5 CBCS mathematics honors. This is the question paper 2020 linear programming and game theory. Question 1a. Suppose that the objective function of an LPP assumes its optimal value at more than one extreme point. Then the, what is the correct option? The correct option is this: every convex combination of these extreme points also gives the optimal value of the objective function. Here, the objective function z equal to cx attains the optimal value z star at the extreme points x1 and x2 dot xk of the convex set capital X of trivial solutions, so that z star equal to cx1 equal to cx2 equal to cxk. Then the convex combination x star of the above extreme points is x star equal to lambda 1 x1 plus lambda 2 x2 plus lambda k xk, where lambda I greater than equal to 0, I for 1 to k, and lambda 1 plus lambda 2 plus lambda k equal to 1. Now cx star equal to c common this, and so this lambda 1 cx1 plus lambda 2 cx2 and plus plus lambda k ck, and this is the cx1 equals z star, so we put here z star common is the lambda 1 plus lambda 2 equal to 1, so this equal to z star. Hence the convex combination x star of these extreme points also give the optimal value of the objective function. Note that the optimal solution of a LPP is either unique or infinite in number. Next question, question 1b. Consider two sets capital X equals to this x1 plus x2 less than equal to 2, 2x1 plus 2x2 greater than equal to 8, x1 and x2 greater than equal to 0. And capital Y is the set of all those y such that mod of y less than equal to 2. Then what is the correct option? Correct option is 2. Capital X is not a convex set, but capital Y is a convex set. Here, for the set capital X, we can draw this figure, this radium, and this is the straight line x1 plus x2 equal to 2, and this is the straight line 2x1 plus 2x2 equal to 8. So this less than equal to 2, so region in this direction towards origin, and this greater than equal to 8, so this region is the in the direction opposite to origin. The given set X is represented by the shaded portion of the figure. Clearly, capital X is not a convex set, because if we take any two a point, this x1 and x2, and join this point in the line segment, does not lie on this convex set. So this is not a convex set. Lies on this set. So this is not a convex set. Whereas capital Y is a convex set, because capital Y mod of y less than equal to 2. This means minus 2 less than equal to y less than equal to 2. If we choose y1 and y2 belongs to capital Y, then mod of y1 less than equal to 2 and mod of y2 less than equal to 2. Let us consider the linear combination of y1 and y2, which is this lambda y1 plus 1 minus lambda y2, true less than equal to lambda less than equal to 1, and then this mod of this is less than equal to 2. Thus the point determined by the convex combination of y1 y2 belongs to capital Y is also in capital Y. Hence capital Y is a convex set. Hence the correct option is 2. Next question. C. Consider a game of size m by n with P of matrix A, small aij, m by n order. If a fixed number be added to each element of A, then the optimal strategies remain unchanged. Value of the game remains unchanged. No, it is not true. The value of the game is decreased by that number. No, both the optimal strategies and the value of the game remains unchanged. It also not true. Correct option is 1. We know this theorem for this game theory. If we add a fixed number k to each element of the P of matrix, then the optimal strategies remain unchanged while the value of the game is increased by k. This is the theorem, important theorem of this of the value of the game theory. So if we denote the original and the new P of matrix mu P of function by EO, E for old and E for new respectively, then EO is the double summation over I and j, Aij, xi and yj, and En double summation over I and j, Aij plus k, xi, yj. Hence, E new equal to double summation Aij, xi, yj plus k into double summation xi, yj. And this equal to EO plus this is the k, this double summation, this equals to 1. So, k. So the constant k does not play any role in selection of an optimal strategy of the game with P of matrix Aij plus k. So correct option is 1. Optimal strategies remain unchanged. Only the value of the game is increased by k. Note that the optimal strategies remain same even when each element of the P of matrix is multiplied by a constant k, while the value of the game becomes k times of the original value. Next question, D. The optimal mix strategies for the player A and B and the value of the game with P of matrix this -4, 6, 2, -3 will be what? Correct option is 1. This is the P of matrix -4, 6, 2, -3. First we find the row minimum. So -4 and 6 row minimum is -4, and this is the row minimum for the second row is -3, and column maximum for the first column is 2, and for the second column maximum is 6. So new lower bar is the maximum of the row minimum, maximin equal to -3, because this is the maximum of this row minimum -4, -3, and new upper bar, that is the minimax, that is the minimum value of the column maximum is 2. So maximin value and minimax value not equal, and the game is not strictly determinable game. There is no saddle point. Let us apply the mixed strategies and now consider the probabilities this x1, x2 and y1, y2 for the maximizing player A and the minimizing player B respectively. So x1 plus x2 equal to 1, y1 plus y2 equal to 1, where x1, x2, y1, y2 are all greater than equal to 0. If V be the value of the game, then the optimal solution is x1 equal to a22 minus a11 by k. Here 2 by 2 matrix, if this matrix elements A11, A12, A21, A22, the formula is that A22 minus A21 by K for x1 strategies, and K is the value A11 plus A22 minus bracket A12 plus A21. So value of the K is minus 15. So x1 is this, and x2 A11 minus A12 by K is 2 by 3, y1 equal to A22 minus A12 by K is 3 by 5, y2 A11 minus A21 by K is 2 by 5, and value of the game V equal to A11 A22 minus A12 into A21 by K is equal to 0, hence the correct option is 1. Next question E, the maximum number of the basic solution for an m by n LPP is correct option is 3, NCM, maximum number of basic solutions for an LPP. Consider the set of m linear simultaneous equations with n unknowns where n is greater than m. This is the matrix form Ax equal to B, where A is the matrix Aij m by n size, and X is the column matrix n by 1, and B is the column matrix m by 1. Assume that the rank of A equal to rank of AB equal to m. AB means the augmented matrix with A and B, and the size of this augmented matrix is m by n plus 1. And let A equal to this matrix B and R. Here B is the basis matrix, size m by n, and R is the m by n minus R. Here B is the matrix is selected m linearly independent vectors. So this is wrong. Actually, this is the m by m matrix. This is the m by m matrix. M by m matrix. This is the square matrix. This is a square matrix, m by m matrix, and we can find the determinant of this value B matrix. R is the, and the B is the matrix, basis matrix selected m linearly independent vectors of A, and X is equal to XB, XR. And XB is the X1, X2, Xm, and XL is the Xm plus 1, Xm plus 2 to Xm. Then Ax equal to B implies, so BXB, and so if we put XR equal to the null matrix O, then BXB equal to B, that is XB equal to B inverse B. XB is the vector corresponding to the basic variable, while XR corresponds to the non-basic variables. The basic solutions XB, O correspond, this is the basic solution is this. The maximum number of basic solution in a system will be NCM, that is factorial n by factorial m into factorial n minus m. N is the number of unknowns and m is the number of equations. Next question. F. Given the system of constraint this and this, correct option is 3. The given system can be written as in the matrix form is 1, 2, 3, 4, 2, 1, 1, 2, and x1, x2, x3, x4, and this is the B matrix 3, 7, and 3, which can be written as A1, x1 plus A2, x2 plus A3, x3 plus A4, x4 equal to B, where A1 is the column matrix, first column is the 1, 2, A2 is the second column, 2, 1, A3 is the third column, 3, 1, A4 is the fourth column, and B is the this matrix 7, 3. Let B1 equal to A2, A4. Here the linear number of linear independent vectors maximum number of is 2, because this is the 2 by 4 matrix. So corresponding to 0, this for this first option, if we choose this 0 and this 0 is the non-basic variables. So B, we can choose the linear vectors for these non-zero elements, these A2 and A4. So we choose here B1 equal to A2 and A4. Then determinant of B1 equal to this equal to 0. So this A2 and A1 vector are linearly dependent set of vectors. So this solution, first solution, cannot be a basic solution of the system. Next, for option 2, this A3 and A4 as a basis matrix. So B2 is the, let B2 is the A1 and A2. A1 and A2, A1 and A2, B2 is the A1, A2 non-zero vectors. So this is the non-zero vectors, 1 and 1. So we choose A1 and A2 is the basis matrix. So to choose here B2 equal to A1, A2. A1, A2 matrix. So determinant of B2 equal to -3 not equal to 0. Hence A1, A2 are linearly independent set of vectors. Then we can find XB2. This is the basic solutions. This being B2 inverse B, that is equal to B2 inverse. If we if with 2 by 2 matrix A1 1 A1 2 A2 1 A2 2, then A inverse equal to 1 by A, interchange the diagonal elements and sign change of the off diagonal elements. So A2 2 A1 1 minus A1 2 minus A2 1. So this is the formula. So we get XB2 equal to -1 by 3 11 by 3, and the corresponding basic solution is this. This is the x1, this is the x2, and other two x3 and x4 equal to 0, non-basic solution. So this is the corresponding basic solutions. But this is the solution, not this. So we option next option 3. For option 3, this is the non-zero vectors, non-zero elements are these x2 and x3. So we can choose basis matrix B3 equal to A2 and A3. So we choose B3 equal to A2 and A3, and B3 not equal to 0, determinant of B3 not equal to 0. So A2 and A3 are linearly independent, and we find the XB3, that is B3 inverse B, is equal to 2 1, and the corresponding basic solution is this 0 x1 non-basic variable 0, x2 2, and x3 1, and x4 non-basic variable 0. Is the correct option is this 3. And option 4 is also not a basic solution, because here there are 3 non-zero elements here, but maximum number of non-zero elements be 2, because maximum number of linearly independent vectors is 2 here. Question G. The optimal solution of the following LPP, maximize this subject to this, is given by this option. Correct option is 1. We here solve this LPP by graphically. We draw this graph 3x1 plus 4x2 equal to 6, x1 plus 3x2 equal to 3, and this is the region convex set is this given by this A, B, C convex set. Solving this point, C point is 6 by 5 and 3 by 5. The shaded region bounded by this constant equation is the feasible region, and the corner points, these extreme points, are A, B, and C. Now we find the value of objective function at these extreme points, and this Z1, ZA at this point A equal to 15 by 2, and ZB equal to 5, and Z equal to 21 by 5. So maximum value is of Z is 21 by 5, which occurs for the point C. So solution is this: x1 equal to 6 by 5, x2 equal to 3 by 5, and Z max equal to 21 by 5. This is the maximizing problem. Question 8. Given the following cost matrix of a transportation problem is this: the cost of transportation according to northwest corner rule is given by, correct option is 3, 125, 125. This is the transportation problem. Cost matrix is this. We apply here northwest corner rule. So this is the uh, origin and the destination, and this the availability, total availability for origin O1 10, and demand for this D1 is 20. So minimum value of 10 and 20 is 10. So we put here this put here 10 and cross this 10, and minus 10, 20 minus 10 is 10. And so here this we off this the row 1 because there is no availability in the origin O1. Next this 15, 14. So 15 and 10, the minimum is 10. So put here in the cell to one cell, put here, allocate here 10. And so the demand for this first column is 0. So this, and this 15 minus 10 is 5. Now, so we off the column, first column 1. Now we have the 2 by 2 matrix, this matrix. This the O2 is the availability 5 units, and O3 40 units, and this the demand D2 is 10, and demand D3 is 30. Now this 5 and 10, minimum of this 5 and 10 is 5, so we allocate 5 in the cell 2 2. So this 5, remove this 5, and this 15 minus 5 equal to 10, we put here 10. So this in the origin O2 there is no availability, so we opt this row, this second row of this second row. Now there are two cells in the third row. This the demand for this 10 and the 30, and 30 plus 10 is 40 is this. So we allocate 10 in the 3 2 cell and 30 in the 3 3 cell. So total cost of this northwest corner rule, by the northwest corner rule, 10 into 2, 10 into 4, 5 into 1, 10 into 3, 30 into 1 is the 125. Next question for I question, for the following cost matrix is the assignment problem. The minimum cost of the assignment is this. The minimum assignment cost is the 17 units. Here first we apply the row operation. So minimum first row, for the first row minimum element is 4, so we subtract 4 from each element of the first row, so 0 0 2. And from the second row minimum element is 7, so we subtract 7 from each element of the second row, so this 3 0 4. And similarly from third row this. Now for column operation, this first column 0, second column we get 0, but third column there is no 0, so we choose the minimum value of the third column is 2, and we subtract 2 from each element of this third column, so this 0 2 and 6. Now we draw the horizontal vertical lines to cover up the all zeros, so we get minimum number of lines is 3, which is the order of the equal to the order of the cost matrix, So we can get the optimal solution this by this from this table. So we allocate. Now we check the single 0 in any row or any column. In the first row, no single 0. Second row, we have a single 0, this 0. So first we allocate this 0. So box this 0. And when we box this 0, encircle or box this 0, then other 0 in this column, we cross this. Next, check the third row, and we get a single 0 in the third row. We allocate this cell, and we correspondingly we cross the this 0 for the corresponding column. and lastly we get this 0, allocate this. So for the machine G1, for the machine G1, for the job G1, this machine M3, G2 is M2 and J3 is M1. And the cost for this diagonal element 6, 7, 4, 6 plus 7 plus 4, that is 17 units. Correct option is 2, 17 units. Next, last question. The following LPP, this maximizing problem, x1 greater than equal to 0, x2 is unrestricted in sign. The dual LPP is this. Duality theorem. First, we write this. Here is the x2 is unrestricted in sign. So put here x2 equal to x2 dash minus x2 double dash, and put here x2 dash minus x2 double dash, and all this. And this is the equation 3x1 plus 4x2 equal to 5. So we write this equation in less than equal to and greater than equal to. 3x1 4x2 equal to 5, 3x1 4x2 less than 5, less than equal to 5 and greater than equal to 5. Now standard form, this maximization problem. So all constraints are of less than type, less than equal to type. So we put less than equal to type, multiplying -1 on both sides, the first constraint, and the second constraint is okay. For third constant, multiplying by -1, so we get the less than equal to sign. Now the dual problem for this maximizing primal problem is minimum W equal to -4y1, 5y2 dash, and -5y2 double dash. And the subject to constraint -2y1, 3 2y1, 3y2 dash, -3y2 double dash. And second constraint -3y1, 4y2 dash, and -4y2 double dash. This is greater than equal to 1, and this is greater than equal to 2. And for third column, from third column, 3y1 minus 4y2 dash plus 4y2 double dash greater than equal to -2. Now we put y2 equal to y2 dash minus y2 double dash. Hence the dual problem can be written as minimization W equal to -4y1 plus 5y2 subject to -2y1 plus 3y2 greater than equal to 1, minus 3y1 plus 4y2 equal to 2, and y1 greater than equal to 0, and y2 is unrestricted in sign. And correct option is 3. Correct option is 3. This completes the MCQ 2020. Thank you.